We start with welcoming Jonathan Kenyon, who's giving us an in-person talk about QuartiCal, an embarrassingly parallel calibration using Numba and Dask.
Thank you so much. Yeah, so as mentioned, I'm Jonathan Kenyon, and I'm going to be talking to you about QuartiCal. I'm currently a postdoc affiliated with Rhodes University and Soreo. Okay, just to start off, I know not everyone in the audience comes from a radio interferometry background. So what do we mean when we talk about calibration? Well, simply the process of correcting a measurement or system to ensure that we get the best possible data out. And specifically in the context of radio interferometry, we're usually talking about solving for and correcting the complex valued antenna gains. An example of what this might do is shown on the bottom of the slide. The left-hand image you may see is an image prior to calibration, and the image on the right is post-calibration, and you can see there's a pretty remarkable difference. So the motivation behind this is that modern instruments and, of course, astronomers require that calibration has to be increasingly flexible, fast, and user-friendly. And to those of you who've designed software, there's always tension between these requirements, and it's very difficult to have all three. In particular, in the context of the 5 Vs, the volume and velocity components are very difficult to deal with, and I hope Rob's introduction earlier convinced you of that. So just to provide some context as to what radio interferometer data looks like, we have a standard format called the measurement set. It's columnar storage backed by Casacore tables. These typically consist of rows and labeled columns, and those columns may somewhat peculiarly contain n-dimensional arrays. Typical data dimensions will be row, which is a combination of time index and baseline, and that will be in the hundreds of thousands to millions. Channel, which is typically between a few thousand and tens of thousands, and correlation typically between 1 and 4. The table on the bottom of the slide is just an indication of how much data you expect to come out of MeerKAT in an hour in about 4K and 32K mode. Bear in mind that this is an underestimate, as it doesn't record all the auxiliary information that also has to be stored. Okay, so well, what is QuartiCal? It's the spiritual successor to CubiCal. If you're not familiar with CubiCal, don't worry about it. It was calibration software I wrote during my PhD. It's a Python-based package, and it makes extensive use of Dask and Numba. I'll get into that in just a moment. And it uses this measurement set-like data structure directly, which is quite compact in memory. The aim of QuartiCal is to be an all-in-one solution to calibration at scale. So this is a little bit of an aside. I'm not really here to talk about QuartiCal's features, more about the computational aspects of it. But just in case it is interesting to you, it supports chains of Jones terms, so those are gains, including both parameterized and direction-dependent terms. We have a robust reweighting scheme re-implemented, which can be used in combination with any gains. We have support for loading and interpolating gains for doing your 1GC. And at present, we have very rudimentary support for baseline-dependent average data, but that is very much a work in progress. And just in general, it is quite highly optimized and parallelized. Okay, so what is Dask? Well, the Dask docs themselves state that Dask is a flexible library for parallel computing in Python. It will be very familiar to you if you've used something like NumPy or Pandas. It has its own collections which mimic NumPy arrays and Pandas data frames. And these so-called big data collections can be used to compose task graphs describing a computation. And then those task graphs can be subsequently allocated to resources by Dask's internal schedulers, so you sort of relinquish the distribution components of the problem. Sort of by default, it supports both distribution and larger than memory computations, and because of this, you can scale from running applications locally on your laptop all the way onto a compute cluster with multiple nodes. So I always think a picture is worth 1,000 words. So I'm just going to take you through some very basic Dask syntax in the hope that maybe you see something that can help you in your application and development. So here I import Dask arrays much as you'd import NumPy. I set up an array of random data, just calling it data. The thing that may be a bit peculiar here is I also specify chunks. So unlike NumPy, where arrays will typically be a monolithic piece of data living in memory, Dask has this notion of chunked arrays. So these arrays are internally broken down into chunks which may be much smaller than the overall size of the array. We can then visualize these things in, say, an IPython notebook, and you can see that in block 2 on this slide. If I simply put the array in the cell, you can see that I get all sorts of interesting metadata out, such as the size of the array, the size of the individual chunks, how big it is, how many tasks there are in producing those chunks, the number of chunks themselves. So that's just to reiterate that chunked nature of the Dask arrays. And then also very interestingly, they're also lazy. And what we mean by lazy, well, if we print the contents of that array, you can see that it doesn't contain any numbers. It's just an array object that's produced by a random sample with a given shape and a certain chunk size. And that laziness is quite important, which we'll get onto. So moving on, we can do operations on these Dask arrays. So for instance, in the top cell here, I take a sum. And again, this is still lazy. If I print the result, there is no result yet. It simply says that there's an array produced by the sum aggregate method. And here you'll notice it no longer has a shape, because if you sum an entire array, you expect to get a scalar out. And indeed, once we call compute, we go from being lazy to being evaluated. And then, of course, we get an answer out. What makes this quite interesting is if we move on to the next block, you can see that we can do things like map blocks, and this allows us to map arbitrary functions over chunks of an array. And so here, for instance, I'm taking the sum of each chunk rather than the sum of the entire array. And again, just visualizing it, it remains lazy, but ultimately we can call compute and we'll get a result per chunk of the input array. So just to summarize, we use Dask arrays to construct task graphs, which in turn are submitted to Dask's internal schedulers, and they handle allocating those tasks to various compute resources. The second technology in QuartiCal is Numba. So from its docs, it states that Numba is an open source JIT, or just-in-time compiler, that translates a subset of Python and NumPy code into fast machine code. So this lets you essentially get the speed of compiled code without compromising flexibility. You can get incredible speed-ups with very little additions, with very few additions to your code. The one caveat here is complex design patterns may be quite difficult to implement. So again, just to present an example, this is just a very simple Python function which determines the nth Fibonacci number. On the left, you can see the pure Python implementation. If we time that 100 times, it takes about 3.4 microseconds per call. On the right-hand side, you can see an example using Numba. In this example, all I do is import the JIT from Numba and then apply a decorator telling it that I'm not using Python and I don't need the global interpreter. And if I run that, you can see that it takes about 200 nanoseconds before. So that's a factor of 17 improvement after adding just 2 lines of code. The final piece of the problem is DaskMS, which is another Python package that exposes measurement set data as Dask array objects living in X-array data sets. On the bottom of this slide, you can see what that might look like. And unfortunately, I'm running out of time, so I'm going to skip over this. So just to show you some results, this is a small local experiment. This is only 2 gigabytes of data. The point here is not to see how this is operating at scale. It's just to give you an indication of its behavior. And you can see that these results are pretty good. So QuartiCal's results are in yellow, CubiCal's are in blue, or teal, and you can see that QuartiCal convincingly outperforms CubiCal in both terms of speed and memory footprint. And again, just because I'm running out of time, I want to get onto the most important experiment here, which is now this is distributed. So this is a MeerKAT calibrator observation at L-band. There's about 100 gigs of data here, so it's a lot more realistic in terms of problem size. We calibrate these and we compare wall clock times as a function of cluster size. There are some details about the cluster just there. And just in terms of calibration, this is just a single gain per time and channel. So what we can see on the left axis is the wall clock time. The right axis is efficiency. That's just measured as the predicted runtime you'd expect if a single node was the optimal performance. And what we can see is the solid orange line has the correct behavior. It's following the dashed orange line, which is the prediction. But unfortunately, it doesn't quite match. We're still digging into why that is the case. But what you should also be able to see is that our wall clock time comes down from around 20 minutes to under 3. For calibrating this calibrator observation. So we're pretty pleased with that. It's kind of proof that QuartiCal is successfully distributing and calibrating MeerKAT scale data. And just a final thing about some caveats. I did not use the measurement set for these experiments. There are a number of reasons pertaining to the lack of thread safety of the measurement set and the fact that Python Casacore, which is the Python interface to the measurement set, does not drop the global interpreter lock. This makes distribution incredibly difficult. And if you want to ask me questions about that, feel free. And then I'll just leave you with my conclusions, and I think it's time for some questions.
Thank you. That's very impressive indeed. So we've got a question that's come in from Discord from Harrow, saying, Am I responsible for making sure the chunk size divides into the Dask array size nicely? What happens if it doesn't?
So Dask doesn't require chunking to be regular. You can have trailing chunks that have a different size. You are responsible in that you need to know that your code does the correct thing if you get a chunk of an unexpected size. But you are not forced in any way to say, divide 9 by 4 and expect that to work.
Okay, thank you. And we have a question from Oleg. If you could step up to the mic, please.
Thanks. I'm very amused by all this Dask developments. I think it's absolutely great, and it reminds me of what we were trying to do with Mac trees with Jan, I don't know, 20 years ago by now. And one thing we already knew about then, but we had no idea how to address. Of course, the execution time of the graph depends very much on how you schedule the execution and which order you evaluate it on. So what if anything, is done about that?
So this is kind of a two-tier problem. So at some level, we do trust to Dask to do the right thing, but then at the same time, we know it doesn't always do the right thing. It's a two-pronged problem. So Dask has an ordering layer where it decides the order in which tasks theoretically should execute. And then inside its scheduler, it also has a decision-making process where it essentially goes, ooh, what am I going to do next? And what can actually cause problems is sometimes that process of going, what am I going to do next, will lead to it doing silly things because it's no longer doing the theoretically correct thing from an ordering perspective. Inside QuartiCal, we have written a plugin that kind of coerces it to do smarter things when running tasks. Essentially, what it boils down to is pinning certain parts of your graph to certain cluster nodes. So that you can be sure that Dask doesn't stupidly move tasks around unnecessarily.
Right, exactly, because data is distributed, so you really want to things stay where they are in the nodes. Okay, thank you very much. Oh.
Thank you, Jonathan. I think we're running out of time for questions, but there's one more question in the, and now 2 questions in the Discord if you would like to go and answer them. Thank you so much again.